LeetCode 689. Maximum sum of 3 non-overlapping subarrays might sound like a puzzle, but it mirrors real-world challenges in streaming analytics. Think of telemetry, rolling dashboards, or profiling bursts where you scan for top-performing time windows. And overlap isn't allowed. The real twist? Thousands of combos to choose from, and only one gives the best total without wasting time. So how do we duck around that brute force swamp? Let's waddle into the simplest approach first, a brute force solution with a tiny optimization feather. We'll pre-compute just enough to dodge redundant work, but in the end, we're still evaluating every possible triplet. Let's sketch it out in code. First up, we grab the array length. We'll refer back to it a lot. Then we build an array to store the sum of each subarray of length k. This gives us fast access to any window's total, no rework needed. To kick things off, we manually sum the first k elements to seed our sliding window. That first total gets dropped into our window sums array. That's our baseline. From here, we slide the window forward, subtracting the element that exits and adding the one that enters. That quickly builds all the window sums we need. We'll track the best total sum we've seen and set up a result holder to store the indices of our optimal 3 windows. Time to dive into the triple nested loop. We try every combo of 3 non-overlapping subarrays. First loop sets the anchor for the first window. Next, we look for the second window. It has to start after the first one ends, so we maintain that non-overlapping rule. Then comes the third. Again, we ensure it's placed after the second. Each full pass gives us a complete triplet to evaluate. To compute the total for this trio, we use our pre-computed window sums, constant time for each lookup. If this total beats our current best, we update the max and stash these starting indices as our new best set. After we've checked all valid triplets, we hand back the result array, the starting points of our chosen windows. This brute force version runs in big O of n squared, which could mean up to 400 million steps for 20,000 elements. Yikes. Space stays at big O of n for the sums, but runtime? Way too heavy for production or interviews. So how do we trim the fat? Instead of checking every triplet, let's reuse work. Prefix sums. Let us skip the repetitive math and zoom in on the good stuff faster. First, we grab the array length and build a prefix sum array. This lets us compute any window sum in constant time. We populate the prefix sum array so each entry represents the total up to that point. That unlocks instant subarray sums later. Next, we build an array to track the best left interval ending at each index, plus a tracker for the highest sum seen so far. As we move forward, we compare the current interval's sum to the best so far. If it's better, we update. Then we store that best index for future reference. Now we build the right side equivalent, starting from the end and working backwards. This gives us fast access to the best right side interval ahead of any midpoint. During the reverse pass, we update the best index when we find a higher sum, and record it for later use. Every step knows the best right window from here on out. With those helpers ready, we declare trackers for the best total sum and our result array. Now we're set to scan all valid middle windows. We run through every valid middle position. For each one, we pull the optimal left and right intervals using our helper arrays, compute the total, and update if it's the best so far. Once we've scanned all possibilities, we return the result, the 3 starting indices that maximize the total sum. This version runs in big O of n time, just 20,000 steps for 20,000 elements. That's featherlight compared to the brute force slog. Space stays at big O of n too, a good trade for the speed we gain. But there's still a bit of overhead. We're scanning for best left and right windows every time. Can we streamline it even more? Let's take a look. First, we compute all subarray sums of length k. These are the pieces we'll assemble into our final triplet. To start the rolling sum, we add up the first k elements and store it. That sets our base for the sliding window. Then we slide across the array. Each time, we drop the outgoing number and add the incoming one, storing the updated sum at the correct index. Now we set up a helper array to track the best subarray from the left. This will help us pick the earliest max quickly. We loop through the sums from left to right. If the current one beats the best so far, we update. Otherwise, we copy the previous best index forward. We do the same from the right, but this time we're after the latest subarray with the highest value, so we fill the array in reverse. While scanning backwards, we update the best index when the current sum is greater or equal. That preserves lexicographic order when sums tie. With both helper arrays set, we can now explore every valid middle subarray, tracking the best total and the triplet that gets us there. For each possible middle, we use the helpers to grab the best left and right. Then we check the total sum and update the result if it's higher. We repeat that for all valid middles, updating when we find a better total. At the end, we've got the best combination. Finally, we return the result, the 3 starting positions that give us the maximum sum without overlap. This approach is big O of n in both time and space, just 20,000 operations and a linear amount of memory. It's clean, fast, and perfectly suited for both interviews and large-scale data. We started with brute force, trimming repeated work with pre-computed sums. But checking every combo still meant big O of n squared, not sustainable as data grows. We leveled up with prefix sums and helper arrays, cutting the redundancy and solving it with a single forward pass. That final version? It's not just optimal, it's how real systems scale. By pre-computing max indices and anchoring the middle, we dodge extra comparisons and keep things slick. Whether you're prepping for FANG or building real-time analytics, this is a must-know technique. Look for similar patterns in other problems and keep sharpening that algorithm muscle.